formerly known as Morgan Fedorchak. Still the same person, still the same pictures of rabbit eyes or whatever else that you're about to see. So I realized a little too late that the title I submitted, although quite descriptive, was maybe not like the most exciting, especially when I saw it on the program listed next to "Help us find a cure." So I need to work on that for next year. But what I'm here to talk about is basically just an update, what we've been doing, where we're at in this process of developing a new eye drop for cystinosis, and just show you the newest of the new data that we have. Before I get started, really, I want to make sure that I thank the people who are involved with this, without whom none of this would be possible. I think that's correct. I don't know. Jorge Jimenez, who is now Dr. Jorge Jimenez. So they have been working on this project long enough that they are now a PhD holding doctor, based all on this research that you'll see today, and Dr. Ken Nischel, who is a pediatric ophthalmologist who first introduced me to cystinosis, and of course, CRF, which is really the driving force behind all of this. So what I'm going to talk about is drug delivery. If you've seen me talk before, you know that drug delivery is basically just improving either the efficacy and or the safety of an approved drug. So we're not really in the business of developing new drugs. We are in the business of taking drugs that exist but have something that's not quite working with them. Either they have too many side effects, or in the case of cysteamine, which also has side effects, but is dosed far too frequently. What we can offer is the ability to increase the amount of that drug that gets where it needs to go, so increase the efficacy, decrease the dosing, and also increase the safety and tolerability of it by using far less drug to achieve those same outcomes. As I talk today, you're going to hear some terminology, or you're going to see some terminology. I just wanted to point out that when we talk about cysteamine eye drops, that is our equivalent to what you would consider cysterin. We don't use cysterin in our studies because we don't really have access to that much of it, obviously, but we can make it something similar that we use in our animal studies. That's our positive control, the thing that we know should work. You'll see some reference to something called SD blank, MS, spray dried. That's how we make the materials, SD, and MS, microspheres. So when you see blank, that's a negative control. That's just the test materials, but no drug at all. And then when you see something called SDCMS, I know it's a lot of acronyms, I'm sorry. This is something that all scientists do. SDCMS, these are spray-dried microspheres with the drug in it, cysteamine microspheres. That is our test material. That's what really matters here, okay? That's what we're developing. So when it comes to drug delivery for eye drops, usually what you get is something like this. You take an eye drop, you put it in, drug concentration goes up, then it falls back down. Then you put another one in and it goes back up, and then it falls back down. And on and on and on with these peaks and troughs again and again. And most frequently what happens is the peaks are much higher than what you really need for it to be effective, are much lower than what you need for it to be effective. So the actual amount of time that you spend in that sweet spot with the right amount of drug getting to where it needs to go is not that much. And that's when you see disease not being treated properly and adverse effects, right? So we're going to try to minimize that. We're going to try to come up with something that hits that sweet spot and stays there for a really long time. Now, for other diseases, a really long time might look like a month or weeks or even days. For cystinosis, a really long time when it comes to eye drops is just one day. Would make a huge difference here compared to hourly drops. So that's what we're targeting, and I'll explain that more in a moment. The way that we're doing it, we have this drug delivery platform that we've been kicking around for a while for things like glaucoma and antibiotics and anti-inflammatory, things that are dosed maybe once a day or several times a day. When Dr. Nischel came to me and said, cystinosis is treated with eye drops every waking hour, I couldn't believe it, that there was actually a medication being administered that frequently at such a high concentration. This is exactly what this type of technology was built for. So I was really excited to put it to some good use. It consists of these drug-loaded microspheres, a gel, and we mix them together. It's a simple suspension. It's like tapioca pudding, basically. And to use it, let's see if the video works. I believe it will. It's a liquid that turns into a solid. So it's administered just like an eye drop, where it forms this pliable, soft gel depot that sits underneath the lower eyelid in a space called the fornix. And that's where you get drug release. The drug is delivered from that little gel over the course of a day, delivering all the cysteamine that a patient would need, in theory. To remove it, there's a number of options here to remove it. What I'm going to show you is just flushing it with saline. Our rabbits don't get much of a say in what we do. But because it responds to a temperature change, so at room temperature it's a liquid, at body temperature it's a solid. If you cool it back down to a liquid, or if you cool it back down to room temperature, it becomes a liquid again. And that's reversible, infinitely reversible. So you can remove it by just decreasing the temperature and flooding that pocket. We've shown before that we can keep this in rabbit eyes for a full month, that it delivers glaucoma medication for an entire month with just one dose. But what we want to show is that it can have some improvement over the current options for cystinosis, corneal cystinosis. We know that it takes a high drug concentration. We know that there's this very frequent administration of eye drops. And on top of that, this is something somewhat unique to cysteamine. We know that it has these really intense storage and stability issues, that it starts to degrade almost as soon as you expose it to any amount of oxygen. Right? And that's a big problem here because it means that you're having to replace those bottles very frequently, that they just don't stay for very long. And that can become onerous on top of all the other issues with this drug. So one of the things that this technology can offer and why this was something that we wanted to pursue is we know with other studies we've shown that we can lower the amount of drug that we administer and still get the same therapeutic effect. So that's going to help with some of that irritation on the ocular surface. We know that we can decrease the dosing frequency by localizing delivery right where we need it to go. Rather than an eye drop that immediately gets blinked out of your eye and you lose most of it, this is going to stay put right where it needs to be, right on the ocular surface. And for those stability issues, we had a very good sense that by freeze drying the materials, which is standard practice for us, we could endow it with some additional stability. So we set out to do this. And our goal when we got started was to come up with this cysteamine microsphere formulation, CMS, that would give us 24 hours of drug release from a single dose. It would be safe, it would be stable, and it would be effective. We made the formulation using spray-dried microspheres, and I would describe how that works, but it's actually pretty boring. But we collect these microspheres and we look at how much drug is coming out over time. And what you see here is essentially what we're saying is that it's enough drug. What we can measure in vitro, so not in a person, not in an animal, but just on the benchtop, it's telling us that over 24 hours, we are hitting the drug level that we'd like. Okay, great. So let's move forward with this. And actually, we published on this. These are what they look like. These are our magical little microspheres. So this was great. We know we have enough drug, but we needed to show other things as well. We needed to show stability. So we did some testing on stability, and what we saw is that we have about a 7-fold increase in how long they can be stored in refrigeration and even at room temperature and still have lots of active drug coming out. Okay, so this is a massive increase in stability. So we know for sure stability, great. I'm not ready to put a checkbox next to effective yet, even though I showed that there's a lot of drug coming out, because that's meaningless if it doesn't actually work in an animal. Okay, we need to take what we can see on a bench and actually see that in a living creature. So that was next. We need to know how much drug is getting to the cornea and what is the effect on crystal density, all right? To know how much drug is getting to the cornea, we decided to use rabbits. Why do we use rabbits? Rabbits have pretty big eyes and pretty small bodies. They are not my favorite animal, not by a long shot. They're not the most fun to work with, but you get a lot of eye for a small body, and it's a great anatomical model for these types of studies. So rabbits it is. So on day 0, we administered the eye drops. If it was the CMS, the gel drop, that was once at time 0 and never again, okay? And then at 24 hours, we ended the study. Either 2 hours, 6 hours, 12 hours, or 24 hours later, those rabbits were done with the study. And then we would take the tissues and look for drug concentration and other endpoints. If it was our equivalent to those cysteamine drops, they got drops once every hour for 12 hours. So it was a 12-fold difference in our treatment versus the standard treatment. And we looked at some safety outcomes, and we looked at drug concentration as well. And here on the right, what you can see, these glowing rabbit eyes, We did some fluorescein staining. We were looking for any signs that there was irritation on the ocular surface. If there's uptake of that stain on the ocular surface, that's not a good sign. We didn't see anything like that. And what's fun is that the gel gets stained too, so you can see it really easily in that fornix. That's what it looks like. It doesn't always glow, but it's cool when it does. One of the things we measured was intraocular pressure, IOP. This isn't necessarily something that tells us the health of the ocular surface, but it's a good indicator for overall ocular health, and it's really easy to measure, so it's something that we went in and did. And what I want you to focus on, yes, we did 2 hours, 6 hours, 12 hours, but your IOP can fluctuate over the course of a day. So if you zero in on 24 hours, this is the longest time point we had, and also it was measured at the same time, both times, right? So the same time of day. So this is going to be the best indicator. And what we see here is there's no real trend. The rabbits, they tend to get stressed out when we're working with them. So you will see some overall pressure increases, but nothing outside the normal range. So nothing to be concerned with here. The next thing we did was we looked at something called facial grimace. So rabbits, they can't talk, but they can tell you a whole lot without speaking. There are these different indicators: ear position, cheeks, their whiskers, where their whiskers are. And one of them is this orbital tightening. And that is a measure on the grimace scale that we can actually look at for whether or not they are bothered by the installation of the drop. So we took pictures of their eyes at every point in time in the study. And what we did was we had a clinician who was totally masked to what we were doing here go in and score this. And I know these are tiny dots and it's, but that's what I'm here for. I'm going to tell you what it means. So basically what we see here is there is a transient increase in that grimace score. The drop goes in and the rabbit kind of winces, right? Similar to what anyone would do when they get a drop put in. But there's no significant difference between any of the groups. And it's gone by about the 10 to 30 minute mark. It drops back down to essentially 0. And you can see on the bottom, so anecdotally, you can see on the bottom that some of them had some really long eyelashes. That's going to increase that orbital tightening a little bit. And you can see on the top, also anecdotal, those eyes were a lot more red. So the cysteamine, we didn't measure it as an outcome, but we saw almost across the board that there was this redness in the eyes, this irritation. We did not see that. We had nice white scleras with our treatment, but we didn't measure that as an official outcome. We did take a look at the eyelids. We wanted to see the health of the eyelid tissue afterwards. We wanted to see the health of the conjunctiva. So, you have this drop that's sandwiched in between those tissues. We wanted to see if they were healthy. And basically, again, we had a masked observer who went in, looked at all of these slides and told us everything looks fine. There's no differences between them. So that was good. And this is all to tell us, is it safe or is it not? The next is drug concentration. So this was a big endpoint for us, looking at how much drug gets into those ocular tissues. And what I want you to look at specifically are the red squares and the blue triangles, all right? I did not choose these little dots. They're hard to see, I think. But what we see is that the red squares are much higher, okay? These are the cysteamine eye drops. We see about a 5-fold increase in the drug concentration in the cornea for that group versus our test group. We still do see drug in the cornea from that single dose of the microspheres. And what you see for sure is at 24 hours, there's nothing left in any of them. And at that 12-hour point, remember, that's when we stopped administering any drops to the rabbits. On the right, you see aqueous humor, similar in concept to where it's getting to. You have it going to cornea, very close to aqueous humor, which is the fluid behind your cornea. This is another place that we're able to collect samples and measure. We went in and looked at vitreous humor. This is further to the back of the eye. This is a way of seeing, are we continuously pumping drug into the eye? And it's a really good sign that we see drug in our test material in the vitreous humor, because it means it's actually having time to travel all that distance. In plasma, we see almost no drug. That's a really good sign. We don't expect to see drug in plasma because there's just not enough of it. But I want to go back to this result in the cornea. You might be looking at this and saying, okay, but they're not matching up. There's way more drug in the cysteamine drops than there is in the test material. What gives? And what I want to explain, hopefully, with this very pitiful drawing that I did, I'm not very good with technology, and if I had tried to draw this like on a computer and make it look nice, it would have taken weeks. And so what you get is this sketch that I made that I think actually does the job. On top, this is what an eye drop is. It's this sawtooth profile. You administer a drop, you get a lot of it, and then it drops back down. You put another one in, a lot, and it drops back down. And on until that 12-hour mark where it goes to 0. There's no drug between 12 hours and 24 hours. Whereas with our materials, yes, it is slower, but it is continuous. So the spaces between, we're not adding anything else. It's continuously presenting drug. And what really matters here is not the maximum concentration. That can be a problem because that's what leads to side effects. What really matters is the area, I hope you can see that little bit of yellow, the area under the curve. That tells us how much drug is actually being presented to that tissue over that whole day. Okay, so the area under the curve is what matters. And you spend at those extreme points, too much drug or no drug at all, that matters quite a bit too. There's that sweet spot that I mentioned before. And these results suggest that we have enough drug over 24 hours for it to be effective. And we know from the other data that it's safe, okay? So this is great, but we still want to check that box and know for sure that it is effective. And to do that, we need to test it in our mouse model, which is the other thing we've been working on. So in our mouse model, we have mice that have crystals in their cornea. We are able to go in and get lots of pictures of these crystals. We spent a lot of time designing a study where we could test these materials in mice. Forget the fact that it says AIM-3. So we were looking to figure out a way to get this gel drop to stay in an incredibly tiny mouse eye. There's a reason why I don't usually work with mice, and it's because their eyes are so tiny. They have almost no volume in the front, and so it's really hard to work with them. We're used to using a 100 microliter drop. We were hoping to squeeze in about a 1 microliter drop. So that's a 100-fold decrease in volume. And we weren't even sure we'd be able to do that. And we tried it, and in fact, we were not able to do it. It pops right out. There's just no ability to keep it in the eye. So then we tried some interesting approaches to getting it to stay in. And what we settled on is what you see on the bottom, where we had this ring where we kind of held it in place. We had to shave the hair off around the mouse eye. We put a collar around them, this Elizabethan collar, and then we covered it with a film. And that was sufficient to keep it in place. So that's good. And we barreled forward, and we designed a study where we would take groups of 5 mice at different time points, and we would replace the drop every day, and we would just measure crystal density over time, and we would look at safety, and we would look at all these measurements. And then after 4 weeks, we would see a reduction in crystal density and everyone would be happy and go home. And in fact, in our control mice, we did see that the mice receiving the cysteamine drops, that's exactly what happened. We saw this reduction in crystal density beginning over that 4 weeks. We saw the results we were hoping for. We saw, nothing weird going on there. So that means that the methods in that sense were working. And then we looked at the full results for the mice that got the cysteamine drop, the gel drop, and it was a little disheartening. There's a happy end to this story, I promise. Or there's hope here. So it was disheartening. We saw that actually the crystal density went up, or so it seemed. We saw the intensity here, the light scattering, it went up, and that should not have happened. And we saw it go up for the blank material too, where there's no drug. It was just bizarre. And then we looked at central corneal thickness, and we saw that the materials were also causing the cornea to thicken. That's even worse. That was never something we anticipated happening here. And then we looked at the eyes themselves, and we saw that they were becoming opaque. The corneas were opacifying. And this is not good, but what this means is that pixel intensity that we saw was not actually anything to do with cysteine crystals. That was this opacity that we were seeing. So what happened? Well, what happened is that gel drop, when we put the mice under anesthesia, they get cold. Normally, it's enough to leave them on a heating pad to warm them up. But when you want to get a liquid drop and warm it up enough to turn it into a gel in their eye, the best way to do that is to blast them with a heat lamp. And a heat lamp right next to their eyes has a tendency to really dry out their eyes. And if you know anything about dry eyes, it's not a good situation. And if you add to that the fact that they had these collars on, and they lacked the ability to do what's called self-grooming. So mice spend about 40% of their day just grooming their face. And that's to keep out debris and all this other stuff that gets in and around their face and their eyes. And we prevented them from being able to do that. So you have very dry eyes, you know, this warm, dry eye, combined with an inability to actually clear anything out from the oculofacial region. And what ended up happening is it caused all kinds of irritation and damage on the cornea. So how do we fix it? We've now taken, only for the purposes of the mice, we are not changing the formulation in any way for how we plan to translate it, but only for the purposes of making this study work. We take those drops, the liquid drop, and we take all the water out of it, which creates a small little film. And then we take that film and we put it in the mice, and that stays put, believe it or not. So we're going to tape the eyes shut. We're going to use some surgical tape to shut the eyes. They're not going to need the heat lamp on their eye because we don't need it to go from liquid to gel. It's going to go from solid to gel. So we kind of reverse the phase transition there. But I cannot stress this enough. This is not the final formulation. This is the same functionality, same drug dose, but you'll still see a liquid drop at the end of this. It's not going to be this film, but we needed a way to keep it in these mouse eyes. So this is what we're doing. And actually to put it in there, so these forceps look pretty invasive, but to keep it in there, what we're going to do instead, and what we've started doing is using, do you know those little like ear wax picker outer kids? I have little kids, so I'm familiar with this. And it has like a light on the end. Turns out those are perfect for sticking tiny bits of material into a mouse eye. So that's what we'll be using moving forward. And the plan here, I like to always talk about the future, understanding that anything can and will happen. The plan here is to complete our mouse study. They're underway right now. We've created the materials. We have the mice ready to go. It's just a matter of getting everything in there and actually testing it. So it's a 28-day process with time points in between, but we've started those studies. And then our next goal is to start making human-grade material, talk to the FDA about what it would take to move into a clinical trial. And the big question mark here, but always our hope, is that very soon we will move this to a clinical trial. And I think that, you know, in terms of the data that you just saw, what is the take-home message here? The rabbit data are extremely promising. I am very confident in those data. The safety, the amount of drug, it's really good. And I've looked at data like that for lots of other drugs and diseases. This is really good stuff. And it's just a matter of getting the methodology right for these mice so that we can make it very clear to anyone else who's interested how well this is working. Those are my thoughts. So I'll wrap it up there. I think I might be a little early. And I'll take your questions if you have them, but thank you so much for your support as always. And hopefully by next year we'll have lots more good news.